I will present a joint work between our group and the Vadim group. So although in the beginning of the session, I pretend like a horse, but I will not talk about Trojan horse attack. I will change the subject a little bit. What we are trying to do is to find a general method to solve the imperfections in the source. The title is Experimental QKD with Source Flaws and Tight Finite-Key Analysis. So in the previous two talks, we heard many about quantum hacking and quantum countermeasures. So let's think about the question, why this happens. I think the second speaker addressed a little bit. The main reason is as follows. The standard security proof of QKD is based on physics plus theoretical models. Quantum physics means quantum non-cloning theorem or Heisenberg uncertainty principle. Besides this, we still need theoretical models. Because if we want to prove a real QKD system, we need to model the device, and then we consider the device model into the security proof. There is no doubt on the physics part, but the problem comes from these theoretical models. Because in practice, the devices have many imperfections. This means the device models are different from the ones assumed in security proof. This gives you a chance to attack the system. A simple example, a secure proof normally assumes perfect single photon source and perfect detector. But in practice, we use coherent lasers and imperfect threshold detectors. This gives you a chance to both attack the source and the measurement device. This slide is summary about recent quantum hacking experiments. For example, the time shift attack, phase remapping attack did by our group, and the famous detector blending attack, channel calibration attack, detector dead time attack, and also the device calibration attack in continuous variable QKD system, and the most recent one, laser damaging attack. What I want to emphasize in this slide is the target part. We can see almost all the attacks working on the measurement device. In other words, the measurement device is the weakest link in a QKD implementation. Okay. Fortunately, once we know this problem, people have found many solutions. One efficient solution I want to talk is called measurement device independent QKD. So if you want to know more or the details about MDI QKD, you can go to the Thursday tutorial session. You can know the basic idea and the recent development about MDI QKD. The key advantage of MDI QKD is it can remove all the detector set channels. This is a quote from a news article in Science. Physics have demonstrated how to close a technical loophole that could have left circuits open to eavesdropper. And this technical loophole exactly refers to the set channels in the measurement device. So MDI QKD removes all the measurement device related set channels. Now the following question we're asking is, what's left for if? The only thing left for if is the source. So today I will also focus on the security issues in the source. One specific problem I'm focused on is called source flaws or modulation errors in the source. I will discuss a new loss-tolerant protocol, and our contribution is both theoretical and experimental. On theoretical side, we perform a finite-key analysis and a decoy set method. For this loss-tolerant protocol, we also perform experimental demonstration. Okay, first is a review about some famous QKD experiments. So far, QKD has demonstrated over 100 kilometers, such as use phase encoding in optical fiber or polarization encoding in free space. In terms of key rate, QKD has achieved over 1 megabits per second. Recently, there is also demonstration about the feasibility of ground satellite quantum communication and also QKD network. Now, the question we are asking about these QKD experiments, are there any secure problem in the source? Today, one specific problem we are looking at is called source flaws. In all previous experiments, the encoding part is assumed to be perfect. For example, in phase encoding, we assume a perfect phase, 0, pi02, pi, 3, pi02. And in a polarization encoding, we assume perfect HD, V, and A. Now, is this true in experiments? The answer is no. Everyone knows in experiment, we have some modulation errors. For example, in phase encoding, we typically use this lithium niobate-based phase modulator. This phase modulator is controlled by some electrical signal, and this signal is obtained from the commercial plug-and-play QKD system. Ideally, we need the optical pulse in the middle, and we need a very flat response in order to get this ideal phase modulation. But in practice, we have some modulation errors on this modulation signal. This will introduce some modulation errors. So this is electrical noise on this modulation signal. Also, in experiment, we have some optics misalignment. This will also introduce another kind of errors. In the end, what we get in practice is ideal phase plus some modulation errors. Also for polarization part. So given these modulation errors, the following question is, owing to these source flaws, the key generated in previous experiment might not be proven secure. So our major contribution in this work is we implement the first QKD experiment that considers source flaws. And our decoy state implementation achieved tight finite key security bounds against the most general attacks in the universal composable framework. So first, let's think about how to deal with the source flaws or modulation errors. Actually, this problem is not new. This problem had already been considered over 10 years ago, such as in the famous JILP security proof. In the security key rate formula, we can consider the source flaw in the estimation of the phase error rate. These two quantities exactly quantify the source flaw. But the problem for JILP security proof is the performance becomes bad. So this is the simulation results. X-axis is the transmission distance over telecom fiber. Y is the security key generation rate per optical pulse. We can see without considering source flaw, a QKD system can tolerate about 150 kilometer fiber. However, after considering source flaw using some standard numbers from the experiments, we can see the security key rate and the transmission distance decrease significantly. So after knowing this problem, the following question we want to ask: does the loss tolerant protocol exist? The answer is yes. Recently, in this work by Dr. Tamaki and his co-workers, also Marcos is sitting there, so they proposed a loss tolerant protocol. The only additional assumption in this protocol is called the qubit assumption. This protocol requires that the 4 BB84 states remain inside two-dimensional Hilbert space. This work shows as long as the 4 BB84 states are qubits, Eve cannot attack the system by enhancing the source flaw through the channel loss. So in other words, in practice, if we can verify this qubit assumption, we can use this loss tolerant protocol to consider the source flaws, and then we can still maintain the performance. This is the simulation results. This is the picture in previous slides. And this is the new simulation results based on the loss tolerant protocol. We can clearly see the improvement of this loss tolerant protocol. After considering source flaws, this protocol is loss tolerant to these source flaws. This work also showed that 3 encoding states have the same performance as the 4 BB84 states. In other words, one of the 4 BB84 states is actually not essentially required. Using 3 states, we can have almost the same performance as BB84. So this is a theory. To use the theory in practice, there's still some questions. On the theoretical side, how to do the finite key security analysis, because the original protocol only considered a asymptotic case or infinite long key. Second question, for laser-based implementation, how to use the decoy state method. On the experimental side, how to quantify the source flaws precisely, and how to verify this qubit assumption. Finally, how to implement the protocol in experiments. In the following talk, I will answer these questions. So our first contribution is rigorous finite key analysis for the loss tolerant protocol. In yesterday's tutorial session, Professor Renato Renner already discussed many details about how to do the finite key analysis. Our work is just based on this framework. So we based on these 2 earlier works by Marco and also Professor Jason Renato Renner. They provide a rigorous analysis for single photon BB84. Recently, by Hugo Group, they extended the analysis to decoy state BB84. So we provide tight security bounds against the general attacks using the entropy uncertainty relation to bound the smooth mean entropies. This is our final secure key rate formula. The first part represents how many detection counts you get from a vacuum pulse. Second part is how many detection counts from a single photon pulse. And this part is the estimation of phase error rate for single photon components. And this quantity quantifies the privacy amplification part. And this is the error correction part. And this term shows the failure probability about parameter estimation and privacy amplification. Finally, this is the failure probability about error correction. So in practice, for the last two quantities, you can choose it from the protocol. You can send a security parameter, for example, 10 to the power minus 10 or 10 to the power minus 20. And for the error correction part, we can directly measure it in the experiments. And for these three quantities, for laser-based implementation, we require the decoy set analysis. So in the following slides, I will show how to do the decoy set analysis for the three-state QKD. Remember that in three-state QKD, we only send three states. And we look at the rectilinear basis, we send the same state as the original BPT4. So for the estimation of the vacuum counts and the single photon events, we can use exactly the same method, because in the following secure key rate formula, we assume we use the rectilinear basis to generate secure key rate and use the diagonal basis for estimation. So we can see these two quantities exactly show the events in the rectilinear basis. So we can directly use some results from original BPT4, such as the famous results by Xiongfeng Ma and his co-authors. The only difference in our estimation is the phase error rate. What we do is we use called reject data analysis. So what is reject data analysis? In original BPT4, when Alice and Bob using different bases, these detection counts are usually discarded in the sifting step. But this reject data analysis shows that this basis mismatch events still contain information, and we can still use this information for estimation. This is exactly what we did, and these two quantities shows the basis mismatch events, which means Alice send a signal in the rectilinear basis, Bob measure in the diagonal basis. Okay, so we can still use this basis mismatch events for estimation together with the measurement events in diagonal basis. When Alice and Bob both use diagonal basis, from these four quantities, we can still estimate the phase error rate. Finally, I want to emphasize a little bit about the three-state QKD. In many QKD implementations, for example, mostly in free space transmission, people use 4 laser diode to generate the 4 BPT4 states. So if you're using 3 states, you can actually save 1 laser diode, and you can only use 3 laser diode. So we can simplify the implementation a little bit. Our next contribution is verify this qubit assumption. So the question is, in a phase encoding system, does Alice prepare a qubit? So qubit means Alice should have the same mode information in all other degrees of freedom except for the phase information. For example, in phase encoding, we require the same mode in spatial, spectral, timing, and polarization. So we find that by using standard filters, we can verify this qubit assumption with high accuracy. For instance, the spatial mode, we know we can use a standard single mode fiber, which has a core diameter about 10 micrometer. We do a simulation to transmit light from a multi-mode fiber to a single mode fiber. We find only after a few millimeters, the light becomes a perfect single mode. And for spectral mode, we can use narrow bandpass filters. If you remember in yesterday's talk by Professor Andrew Shields, he already showed that using commercial off-the-shelf bandpass filter, we can approach to the fundamental limit of time bandwidth product. So in other words, if we're using commercial narrow bandpass filter, we can guarantee the spectral mode. And also for timing, we can do a careful synchronization. Finally, for polarization, we can use polarizer or polarization beam splitter. So in practice, for the finite extinction ratio about a standard polarizer, we calculate the fidelity between different encoding states. We find the fidelity is upper bounded by 1 minus 10 to the power minus 7. So in summary, we can guarantee this qubit assumption with high accuracy. So our next contribution is quantify the source flaws. We do the quantification in the commercial plug-and-play QKD system. This is our setup. So in Alice encoding part, we ask Alice to generate different kind of encoding phases, and then we use the interferometer to measure phase. So from the detection counts on these two detectors, we can exactly know the phase modulated by this phase modulator. This is the detection counts obtained from the ID500 QKD system. Finally, we found in the commercial system, in ID500, the error is upper bounded by 0.127. And for Clavis 2, the error is upper bounded by 0.147. Our final contribution is the implementation of this loss tolerant protocol. Our implementation is still based on the plug-and-play system. So as the first speaker, Shihan already discussed how this system works. So I will ignore the function of the system. So we use ID500 system, which is the first generation of plug-and-play QKD system. What we do is we do software modification to control the phase encoded by Alice. In 3-state QKD, we only send these 3 states. And in 4 BBT4, we send these 4 BBT4 states. This is our counts obtained from the experiments. We do the experiment over 50 kilometer telecom fiber. We send the optical pulse about 5 times 10 to the power 10. I will consider a secure parameter about 10 to the power minus 10. And the difference in our experiments is we directly measure the counts instead of the probabilities, which is also called gains in previous experiments. And also we record this reject data. So basically the basis mismatch events. When Alice used rectilinear basis and Bob used diagonal basis, we still record this count for the estimation of the phase error rate. So using this count, this is our final results. The first 2 quantities are estimated from the decoset method, and we obtain a quantum beta error rate about 3%. The estimation of phase error rate about 11% for 3-state QKD and 6% for BBT4. And the difference in this estimation of phase error rate is mainly due to the finite data analysis. We perform a numerical simulation. So if we run the experiments longer and generate more data sets, we finally find the estimation of phase error rate is very close between 3-state and BBT4. Finally, we generate secure key over 2 megabits, and this key, the security of this key considers source flaws, and it can be against general attacks by eavesdropper. This is the numerical simulation results, and for the right solid curve is the results without considering any source flaws. And this green dashed curve is after considering source flaws in our QKD system. We can see, based on loss tolerant protocol, our commercial system can tolerate about 60 kilometer fiber. However, based on JILP, the system can only tolerate about 10 kilometer. So we can clearly see the improvements of the loss tolerant analysis, and also our experiments quite match to the numerical simulation. So in summary, the loss tolerant analysis can loss tolerant to source flaws. Finally, some discussion about future directions. So far, the source flaw only considers in BB84. So how to consider the source flaws in practical MDI QKD, and also a standard assumption made in both MDI QKD and also the full device independent QKD is the Alice and Bob do not have any unwanted information leakage. So how to guarantee this assumption? For instance, in the 2 previous talks, they talk about the Trojan horse attack, and we have some countermeasures. But the question, are there any other attacks? And maybe there's some other kind of attacks to violate this assumption made in both MDI QKD and also in fully device independent QKD. And also how to consider the modulation errors in continuous variable QKD. There is still another direction for study. So in summary, a QKD implementation should consider the source flaws and should employ a regular security analysis. Our experiments make practical QKD, loss tolerant to source flows over 50 kilometer telecom fiber. And we show that the 3-state QKD is feasible in practice. For more details, you can visit this reference and also two close related works in this two reference. All right, thank you very much for your attention.
Well, maybe I start with one question. You made quite a strong statement on your qubit assumption. So you said with these different measures, filters, and so on, you can guarantee that you have really qubits at the source. So this means that there are no side channels.
Yes.
And now in your last slide, you kind of, for future work, you say protect Alice from leaking unwanted information. Isn't this a contradiction to what you said before? Because you pretty much excluded this possibility that Alice leaks.
So here I mainly want to talk active weave, because here we kind of most focus on the passive weave. So we don't consider if there's some information coming out of the Alice.
You mean by channels which completely independent of the optical fiber, some radio emitter or whatever?
Right. Like some reflections from the, you send a light to come into
okay,
Alice.
That's this kind of Trojan horse attack. Okay.
Yeah, like this kind of Trojan horse attack. I didn't consider that.
Okay, thank you very much.
It's about it's a question about the phase error estimation between the 3-state protocol and the BBT4. Because I didn't know the numbers, and I was surprised to see so big difference, because we know in the asymptotic case they should be the same. So now we know that with the 3-state protocol we can get exactly the same phase error estimation as with the BBT4. But however, in the finite-key analysis, with the data block size that you consider for the simulations, there is a big discrepancy. Can you tell us more about this? So do you think there is a way to improve it? And also, when do for which sizes of blocks they start to become more closer?
I think the main reason because in 3-state QKD, if you want to estimate the phase error rate, you involve more quantities, right? You not only use the data obtained when Alice and Bob both use diagonal bases, you also use the quantities when Alice and Bob use different bases. But remember that once you have a new quantities, there have some fluctuations. You add some fluctuations. So in the end, if you have more quantities for estimation, you involve more fluctuations. But I found that this is not a problem if you use a high-speed system. Because right now I use a plug-and-play system, I can't run the system quite longer. However, if you use a 1 gigahertz system, I found you only run the system about 20 minutes, you can almost have the same estimation between 3-state QKD and the BBT4.
So that means that even with relatively short data blocks, you can already get the same.
That's right.
estimation.
If you have a, let's say, 1 gigahertz repetition rate system, you only need 20 minutes. Then the estimation is the same.
Okay, thank you.